Imagine you're trying to fit the engine of a massive heavy-duty freight train into a tiny, battery-operated remote control car.
Oh, man. Yeah, that's not going to end well.
No, right? I mean, you want all that incredible pulling power, all that performance, but the physics they simply don't align.
Right?
There's no space, and the battery would drain in like a fraction of a second.
Yeah, instantly.
And that friction between raw capability and physical constraints is, well, it's essentially the crisis we're facing right now in the hardware deployment of convolutional neural networks.
It really is. It's the defining bottleneck of edge computing right now.
Yeah.
We've built these highly capable CNNs, but their appetite for memory bandwidth and compute cycles it's completely ravenous.
Right, which creates a massive barrier when we try to move inference away from, these massive server farms down to the actual devices that are collecting the data.
Exactly.
Huh.
Like your phone or a smartwatch.
Which is exactly our mission for this deep dive. We are looking at a really fascinating research paper today.
Oh, this one is wild.
It is. It's by Christos Kirkou, and it's titled Towards Efficient Convolutional Neural Networks with Structured Ternary Patterns.
Catchy title.
Always right. But the core of this research is about solving that exact bottleneck. How do we shrink these power-hungry models down so they comfortably fit into a smartwatch or a mobile phone or a drone without losing the accuracy we rely on?
Because that's the trade-off, usually.
Exactly. And the proposed solution here is, well, it's wild. Instead of waiting for Moore's law to give us a better microchip, Kirkou suggests we teach the network to process spatial features using only 3 discrete values.
Yeah. -1, 0, and 1.
Just 3 numbers.
It feels almost aggressively simple when you first hear it,
It really does.
But if you are building applications that require real-time, on-device inference, this approach is, well, it's a paradigm shift.
Why is that? Why should the average person care about this?
Well, we're talking about 0 latency, for one, and absolute data privacy, because nothing gets beamed up to a cloud server to be processed.
Oh, right, because the phone is doing all the thinking itself.
Exactly. And it ends that constant thermal throttling, when your phone gets super hot and drains the battery because it's trying to run a heavy vision model.
Oh, yeah. My phone feels like it's going to melt sometimes.
Right. So this prevents that.
Okay. So to really grasp why restricting weights to just -1, 0, and 1 is such a massive leap, we should probably evaluate how we've been trying to solve this problem up until now.
Yeah, that's a good place to start.
Because the current playbook for forcing CNNs onto edge devices is basically just a series of post-training compromises.
Compromise is the perfect word for it, really.
Yeah.
The traditional pipeline is to train a massive, over-parameterized model first, and then try to hack away at it after the fact.
Right.
You see 2 main strategies heavily utilized in the industry: quantization and pruning.
Right.
And both of them carry some pretty significant baggage.
Yeah, so let's talk about quantization first. That's the process of downcasting those 32-bit floating point weights into lower precision formats, right? Like INT8.
Exactly. You're squishing the math down.
Right, so it's kind of like trying to play a complex piece on a grand piano while wearing thick winter gloves.
I love that analogy.
Yeah, you're hitting the general area of the notes and you're saving a massive amount of memory footprint, but you completely lose that fine-grained mathematical precision.
You do.
Yeah.
And the physical reality of the hardware is that, well, while INT8 operations are faster, you introduce this massive headache known as the accuracy gap.
The accuracy gap.
Yeah. The model just behaves differently than it did during training because you've altered the weights.
Right, because of the gloves.
Exactly. And then you have pruning, which is the other common method, where you're basically zeroing out the weights that supposedly don't contribute much to the final activation map.
You're just snipping them out.
Snip-nip, yeah.
But with pruning, don't you end up with these highly sparse matrices, like Swiss cheese networks?
Very much so.
And from what I understand, unless you have specialized hardware accelerators designed to handle sparse matrices, standard GPUs often don't even see the performance gains you'd expect.
No, they don't.
Because the memory access patterns become completely irregular.
Right, precisely. The GPU is still checking all those empty spaces. And the shared nightmare for engineers using either of these post-training methods is the sheer unpredictability of the degradation.
Oh, because you don't know what's going to break.
Right. You can't easily forecast which specific convolutions will break when you quantize or prune them.
Wow. So what do you do?
Well, you enter this punishing cycle of iterative retraining. You compress the model, you realize the accuracy on your validation set just tanked. So then you freeze certain layers, fine-tune the remaining weights, compress again, and cross your fingers.
That sounds miserable. It's a massive sink of computational resources just to get a model back to a functional baseline.
It is. It's a huge waste of time and money.
Which I guess is why we've seen this push toward the absolute extreme end of the spectrum, right? Binarization.
Oh, yeah. The binarization extreme.
Like, if we're going to compress, why not just go all the way down to ones and zeros? Which, to me, is basically like trying to rewrite a dense, sprawling 1,000-page textbook using only a 100-word vocabulary.
Yeah, that's exactly what it is. And the results of binarization reflect exactly that loss of vocabulary.
I would imagine.
The paper highlights that vanilla binary networks suffer a brutal accuracy degradation. We see an average drop of over 20% on standard vision tasks compared to their full precision counterparts.
20%. That's huge. That makes the model practically useless for a lot of tasks.
It really does. But the real irony of binarization is the training process itself.
Oh, because of the gradient tracking, right.
Exactly. You can't easily backpropagate through discrete binary steps.
Right.
So engineers have to use workarounds, like the straight-through estimator, keeping a hidden set of full precision floating point weights in the background just to calculate the gradient updates.
Wait, really?
Yeah. And then they discretize them for the forward pass.
Yeah.
So you're still paying a massive computational tax during the training phase.
So you're not even saving compute when you train it?
Not at all.
Okay.
It's a total false economy.
Wow. Okay, well, that brings us perfectly to the core innovation of Kirku's paper. If post-training compression is an iterative nightmare and binarization destroys our accuracy while still taxing our training servers, we clearly need a native solution.
We need something built from the ground up for this.
Right. And the paper proposes injecting this efficiency at the initialization phase using structured ternary patterns, or step blocks.
The step blocks, yeah.
And the fundamental constraint here is that these specific filter weights are locked into a ternary system, so just -1, 0, and 1.
Right.
I want to look at the hardware mechanics of this, because this is where the theoretical math hits the silicon, and it blew my mind when I realized what was happening.
The physical hardware architecture is absolutely where this gets brilliant.
So in a standard convolutional layer, the arithmetic logic unit on the chip is performing millions of multiply accumulate operations, right?
Millions of them, yes.
You have a pixel value, and you multiply it by a floating point weight.
Right, like 0.7432 or whatever.
Exactly. And at the silicon level, multipliers take up a significant amount of physical real estate, right? And they draw a lot of power. They're complex circuits.
They're very heavy components on a chip.
But if your filter weights are strictly restricted to -1, 0, and 1, you don't actually need a multiplier circuit at all.
Nope. You can bypass it entirely.
Because anything multiplied by 0 is 0, so you just skip it.
Yep.
Multiplying by 1 is just passing the value through.
Exactly.
And multiplying by -1 is just flipping the sign.
It becomes a multiplier-free operation. The chip is literally only executing basic addition and subtraction.
That is incredible.
It is. When you eliminate multipliers from the hardware equation, you save massive amounts of die area, and your thermal footprint just plummets.
Because you aren't running those power-hungry multiplier circuits.
Exactly. You can process convolutions significantly faster while barely sipping power from the battery.
Okay, I follow the hardware advantage entirely. That makes perfect sense. But I'm stuck on the word static here.
Yeah. The static weights.
The paper indicates that these ternary filters are generated before training even begins, and they remain fixed.
They don't change.
Right. So if we aren't allowing the network to backpropagate and update these specific weights, aren't we basically just hard-coding the AI?
That's the big question.
Because, I mean, the entire philosophy of deep learning over the last decade has been that the network will learn better feature representations than humans can hand design. Doesn't locking in static weights kind of hobble the model right out of the gate?
It is the most valid criticism you can level at this approach.
Sure.
And it's exactly where the deep learning community initially pushed back.
I bet.
If you initialized a layer with just random static ternary values, it would absolutely cripple the network's ability to learn.
Right.
But the operative word in STEP is structured. These aren't random.
Okay.
Kirku is leveraging established, highly optimized computer vision priors to generate these patterns.
Priors, so things we already know work.
Exactly. Specifically, center-symmetric local binary patterns, or CSLBP, and Haar structured features, HSF.
Okay, so we're basically reaching back into the pre-deep learning era of computer vision here,
We are.
because we used to rely heavily on handcrafted features before we had the compute to let CNNs figure it out themselves.
Exactly. Back in the early 2000s, this is how we did it.
So how do these specific structured patterns actually process the pixels? Like, how does a CS-LBP filter work mechanically?
Okay, so think about a standard 3 by 3 pixel grid moving across an image as a convolution window.
Okay, got a 3 by 3 grid in my head.
A CSLBP filter compares the intensity of opposite pixels across the center of that grid.
Oh, opposite pixels. So it looks at the top left pixel versus the bottom right?
Yes, and the top right versus the bottom left. It's basically calculating the gradient across the center point.
Okay, so if the top left and bottom right are both dark, but the top right and bottom left are bright, the filter fires because it detected a sharp shift in contrast.
Exactly.
And it does that regardless of the specific lighting conditions, right?
Yes. Because it's comparing relative differences rather than absolute pixel values, it acts as an incredibly robust illumination invariant edge and corner detector.
Oh, that's smart. So it doesn't matter if the image is in bright sunlight or deep shadows, the relative contrast across those diagonals holds true.
Exactly. It's looking for the shape, not the brightness.
Okay, and what about the other one? The Haar structured features, or HSF?
So HSF operates on a slightly different spatial logic. Instead of comparing individual pixels on a diagonal, Haar features look at the contrast between adjacent rectangular regions.
Rectangles instead of pixels.
Right. Imagine a filter that adds up all the pixel values in a left rectangle and then subtracts the sum of the adjacent right rectangle.
Oh, okay. Which is essentially how early facial recognition algorithms worked, right?
Yep.
Like detecting that the bridge of the nose is generally brighter than the sunken areas around the eyes.
Spot on. It's a spatial frequency filter. It is remarkably efficient at capturing abstract structural patterns and uniform regions.
Okay, so I'm starting to see how this comes together.
Yeah, so by layering CS-LBP blocks to find the sharp edges and HSF blocks to define the broader structural regions, you are handing the network a hyper-optimized toolkit for spatial awareness.
We aren't hobbling the network at all. We're giving it a head start.
Exactly. We are relieving it of the burden of having to relearn basic geometry from scratch on every single training run.
That framing makes a lot of sense. You're giving it the fundamental building blocks of vision right out of the box.
Yes, instead of making it guess until it finds them.
Okay, but theoretical elegance only gets you so far.
True.
The real validation is in the benchmarking, and the data in this paper is pretty staggering, honestly.
It really is.
Kirku integrated these step blocks into major architectures, VGG16, ResNet 50, MobileNet v2, and EfficientNet, and ran them against datasets ranging from CFAR 10 all the way up to ImageNet 16.
And the reduction in the parameter footprint is immediate. When you replace standard convolutional layers with these static step blocks, you are fundamentally removing trainable parameters from the board.
Because they're static, so they don't count towards the trainable memory footprint.
Exactly.
So looking at the VGG16 architecture, when it was modified with STEP, it experienced an 82% reduction in storage size. 82%.
It's massive.
You're taking a massive heavyweight model and instantly crushing its memory footprint. But I guess a more important metric is how that compression impacted the classification accuracy.
And this is where those structured priors prove their worth.
Yeah.
Despite shedding up to 80% of their parameters, the step-modified networks only saw an average accuracy drop of 3.1% compared to the full precision floating point baselines.
Only 3%. Compare that to the 20% drop we discussed with vanilla binarization earlier.
Right. You're retaining over 96% of the model's accuracy while freeing up massive amounts of computational bandwidth.
That's incredible. And I actually noticed a fascinating anomaly in the ImageNet 16 results in the paper.
The ResNet anomaly.
Yeah. The ResNet architecture utilizing stepped blocks actually showed a marginal improvement in accuracy over its heavyweight counterpart.
It did.
How is that even possible? How is a model with a fraction of the parameters and static, unlearnable filters outperforming a fully dynamic network?
It comes down to regularization.
Okay.
A fully parameterized ResNet on a smaller dataset like ImageNet 16 has so much capacity that it runs a high risk of overfitting.
Meaning it just memorizes the training data?
Exactly.
Yeah.
It starts to memorize the noise in the training data rather than generalizing the underlying features. By stripping away millions of parameters and locking in those robust edge-detecting step features, you are essentially forcing the network to rely on fundamental spatial geometry. Okay. The reduced capacity acts as a strict regularizer, preventing the network from getting lost in the noise. which ultimately improves its performance on unseen validation data.
Wow. It's almost like putting blinders on a racehorse to keep it focused on the track instead of the crowd.
That's a great way to look at it.
But, image classification on standard data sets like ImageNet is a very controlled environment.
It is. It's lab conditions.
Right. And the climax of this paper is the real-world deployment test. They didn't just benchmark this in a lab. They built a custom architecture called StepDet and deployed it for unmanned aerial vehicle object detection.
Which is so cool. The UAV test is the ultimate proving ground for edge AI.
Why is that?
Because the environmental and hardware constraints are absolutely merciless on a drone.
Oh, I bet. I mean, you're dealing with high altitude, which means the objects you're trying to detect, like vehicles on the ground, are tiny.
Tiny, often occupying just a few pixels.
And you have constant motion blur, erratic rotation from the drone's flight path, occlusion from trees or buildings. And on top of that, the compute payload on a drone is strictly limited.
Yes.
Because every ounce of battery power diverted to the neural network is power taken away from the flight rotors.
Exactly. If the model draws too much power, the drone literally falls out of the sky.
Wow.
And if the processor runs too hot, it thermal throttles, you drop your frame rate, and you miss critical detections.
So it has to be perfectly optimized.
That is why the StepDet architecture is such a breakthrough here. The entire model was built around these structured ternary patterns, resulting in a microscopic footprint of less than 1 million parameters.
Under 1 million? That's tiny. I have the metrics here. Despite being 40 times smaller than standard detection models, StepDet went toe-to-toe with heavyweight architectures like Darknet 19.
40 times smaller.
And it achieved highly competitive mean average precision and intersection over union scores.
It's amazing.
It's basically like trading a theoretical Formula One car that requires a pit crew and a wind tunnel to function for a rally car that actually survives the dirt track, runs on standard fuel, and still finishes within a second of the lap record.
It is the definition of high-yield efficiency. You are trading a nearly imperceptible sliver of theoretical maximum accuracy for a monumental leap in real-world deployability.
Right.
And because the spatial priors are hard-coded, the few parameters that do remain trainable converge much faster.
Which naturally leads to the next phase of this research, right?
Yeah, the automated design.
Right. If human engineers can manually swap out layers in ResNet or handcraft a StepDet architecture and achieve these results, what happens when we automate the process?
Now we're talking about the future.
Right. The conclusion of the paper points heavily toward neural architecture search, or NAS.
NAS is the logical evolution here.
Yeah.
Right now, a human researcher has to intuit where a CS LBP block belongs versus where an HSF block belongs within the network hierarchy.
It's trial and error for humans.
A lot of trial and error. Neural architecture search utilizes machine learning to design the network itself.
So the AI builds the AI.
Basically, yeah. By creating a search space populated entirely by these highly efficient step blocks, we can let an algorithm discover the optimal arrangement for a specific task.
So instead of training a bloated network and retroactively trying to compress it with quantization and dealing with that whole mess, the AI natively builds a lean ternary machine from scratch.
Exactly. The architecture is inherently optimized for the hardware from day one.
That's so smart.
And this has massive implications for fields like federated learning, too.
Federated learning. Okay, so that's where you are training a model across thousands of decentralized edge devices simultaneously, right?
Yep, like a fleet of cell phones. The devices compute the gradients locally and then send just the weight updates back to a central server.
And bandwidth is always the bottleneck there. If your model has 50 million parameters, transmitting those gradients drains the radio antenna battery on a mobile phone incredibly fast.
Oh, it destroys the battery, not to mention the network latency.
Right. But if your model is built on step blocks...
A huge percentage of those weights are static.
Oh, they never change.
They never change, so they never need to be transmitted.
Wow.
The amount of data required to synchronize a federated network just plummets. It makes privacy-first, decentralized AI vastly more practical at scale.
That is a complete philosophical shift. For the last 10 years, the prevailing thesis in deep learning has been brute force.
Brute force everything.
Throw more data at the model, scale up the parameter count, and build bigger silicon to handle the matrix multiplications.
But this research is proving that we don't necessarily need brute force.
By reintroducing elegant fundamental math, literally just addition and subtraction and structuring it around proven visual priors, we can achieve top-tier performance on a fraction of the compute budget.
It was a return to intelligent design over raw scale. The efficiency gains we are seeing here aren't just incremental, they are structural.
So, to recap the core insight for anyone looking at deploying models to the edge. Step blocks lock specific convolutional filters into a ternary system of -1, 0, and 1, completely eliminating the physical need for power-hungry multiplier circuits.
Yes.
And by structuring these static values into proven edge and spatial frequency detectors, models can shed up to 80% of their parameters without the catastrophic accuracy loss associated with standard binarization, all while completely bypassing the headaches of iterative retraining.
It is a literal roadmap for building hyper-capable vision models that actually respect the physical constraints of everyday devices.
It fundamentally changes the equation for edge deployment.
It does.
Yeah.
And it leaves us with a rather provocative question about the broader AI landscape, I think.
What's that?
Well, we've just explored how injecting hard-coded non-learnable priors, like these spatial geometry detectors, gives computer vision models a massive head start, right? Saving immense amounts of compute. So as we watch the parameter counts of large language models spiral into the trillions, we have to ask, are there equivalent structural priors for language?
Oh, wow.
Are we currently burning millions of dollars in server compute, forcing LLMs to learn the fundamental rules of grammar, logic, and syntax from scratch through raw statistical association?
When we could just give them the rules.
Exactly. Could we build hard-coded logical structures directly into their architecture from day one, skipping the brute force entirely?
That is a fascinating thought. Are we just wasting compute teaching AI how to read when we could just hand it a dictionary?
Something to think about.